First, let's go through the most common solutions. First off, we have repeaters, also called BDAs or bidirection amplifiers. These are used in small venues, typically less than 100,000 square feet, and they are used to expand coverage. A repeater uses a rooftop antenna to draw capacity from a nearby macro cell as the RF source, and just rebroadcast the signal throughout the facility. Donor cell site capacity is shared with the external traffic and is not dedicated to the venue or the building. DAS antennas and splitters provide coverage to various locations inside the building from the input of the BDA. BDAs are by far the most simple and straightforward of in-building coverage extension solutions. However, they come with their own set of challenges. For example, a direct line of sight with the donor antenna is a must, and sufficient gain is required to compensate for the cables and losses inside the building. However, the radiating cable or antennas must be kept away from the BDAs themselves to avoid amplifier oscillation. Also, sufficient separation must be kept between the uplink and downlink frequencies, especially in higher DCS bands, where you would need something around 30 to 60 MHz of separation. For large venues, however, the big problem with traditional BDA solution is the large amount of large diameter coaxial cable that is required to cover the entire building. This is more expensive, for example, relative to fiber or Cat5 cables. It's heavy and requires special skills to install. Typically, the building infrastructure is not equipped to handle this specialized cable, and the installation can be costly, especially considering that no added capacity or capacity offloading is included in this case. The second solution would be small cells. Small cells are low-powered radio access points, typically less than 1 watt of output power. These improve the indoor and outdoor coverage and increase capacity to offload traffic without requiring much installation. Deployments for small cells began in 2013 and are ramping up exponentially since then. femtocells, picocells, and microcells operate on a different principle. These small cell solutions create a network of their own of discrete cells, each with a fixed and fairly limited capacity and coverage. And of course, DAS. A DAS is a network that distributes the RF signal across antennas that are installed throughout the facility. A small cell, a BDA, or even a dedicated BTS can be used as the RF source for the DAS. DAS systems are primarily used to modify, improve, or extend coverage of a site, typically in large buildings, stadiums, public spaces, airports, enterprise, and outdoor environments. A DAS system supports the designer to apply a strict zoning to the venue or building where the system is going to be installed. This enables DAS to be used in tightly packed venues, such as sports stadium, where 50,000 users or more may be downloading data, posting photos, or the likes. The system also provides the ability to dynamically adjust and to change in the capacity demands per area and per carrier. DAS solutions are also multi-frequency, able to handle 2G, 3G, and 4G commercial frequencies that operate in the range from 700 all the way up to 2500 MHz or more. This is in addition to public safety frequencies, whether in the 700, 800 MHz, 400 MHz, or all the way down to UHF and VHF frequency bands. femtocells remain exclusively a single frequency, single carrier solution in comparison. DAS was designed to scale in order to meet the growing needs of the network. By adjusting to the power of the antennas, a single BTS can serve up to 1,000 or more users and provide coverage radius of several miles. Picocells and femtocells, however, were designed to deliver coverage and capacity over a relatively small area, similar to a Wi-Fi access point. Adding more coverage requires installing more small cell nodes. While in following sessions we are going to go into more detail about what type of in-building system would be more suitable for which application or which case. However, a rule of thumb is that for defined small range applications, small cells provide excellent quality of service. Their short range and ability to detect and adjust other small cells to the area help negate multi-cell interference. This does not mean that small cell solutions are immune to service issues. When used for larger applications involving dozens of nodes, the potential for interference increases significantly. The sheer number of cells in use and the carrier's inability to control their position and use, as well as issues with handoff between these ad hoc cells and the overall network, create significant challenges in spectrum and interference management. Small cells can also experience interference problems when using low-band spectrum and diminished range when using high-band spectrum. In comparison, for DAS versus small cell solutions, cost is perhaps the most curious characteristic of all. One argument against DAS has been the high cost of deployment with RF engineers. In fact, when deploying for smaller and lower density applications, DAS may not be the best choice. The reason is simple. DAS was not designed to excel in these type of scenarios. In order to support a few dozen users and a single carrier, small cell may be the better choice for these applications. As capacity and coverage requirements increase, however, the cost analysis begins to tip in favor of DAS. For large deployments, it is much less expensive to deploy a DAS for in-building coverage than to deploy dozens or hundreds of picocells or femtocells. Operating expenses are lower as well as in a multi-carrier environment. The challenge for the network operator or owner is determining precisely where that tipping point is. In addition to cost, one must also consider the importance of functional needs, interference control, scalability, and other characteristics. This will be covered in more detail in coming sessions.